The first and the foremost, we will check with the outliers. I have given some random numbers, some assuming a hypothetical data, where you have a condition with some variables which you have measured. Now in this case, so you can see that you have in the B column some data. And just in order to see that how we can check the outlier, I will open SPSS. Fine. So what you will see, yesterday if you remember in the when I showed you that how you can put the data in SPSS, at that time I have showed you that there are two pages in the data editor of SPSS. First is the variable view and second is the data view. In the variable view, you have a treatment, that is the first row and first column, and in that you will see that it's a nominal measure, right? It doesn't matter for outlier, it is not important. You just understand that this is a nominal, and then you have some values over here. So in this value, 1 represents control data. Okay. Similarly, you have variable 1, and in this variable you have, since it's a numeric data, it's in the scale, right? Scale measure. And then you have the second variable, which is again in the scale measure. Once you create this variable view with nominal in the treatment and scale in the variable, you will see in the data view that the treatment and variable 1 and variable 2, right? Now, what is our aim? Our aim is to see whether there is an outlier in this data or not. So to check the outlier, what I will do is, I will go in Analyze, I will go in Descriptive Statistics, and in Descriptive Statistics you go in Explore. Though there are several other ways to find out, but I will just prefer this Explore. Once you go in Explore, you have a factor which is your treatment, and then you have a dependent list, that is your variable 1 and variable 2. Now you can do independently variable 1 and variable 2, or you can do all together. Let us do one by one. We go in dependent list. In this particular box, you will see that there is a statistics option, right? And then there is an outlier. So you click this outlier, continue it, go in plot. This is not so important, so we can just, for now we will just leave it. So important is just to go in statistics, outlier, continue, right? In here, you have two options of display. One is both statistics and plot. Though we are not concerned about other statistical analysis which the software is doing right now, we will leave it as both and we will click OK. As I said yesterday, that SPSS gives you output in a separate document, which is this. It gives you basic descriptive statistics. First is that the case processing. So since it's a random data, just in order to show you that how the outlier looks like and how you can identify it, I have left everything as such. So here you have 11 numbers. So it means your sample size is 11, right? It gives you some descriptive statistics, mean, median, mode, minimum, maximum, range, variance, skewness, kurtosis, everything. Again, do not look into this descriptive statistics right now. I will show you with some other file. Okay, go down. and then you will see a box plot here. Let us focus ourselves in this box plot. In this box plot, we will see that you have a median, then you have whisker. It means till the place in the up or in the maximum and the minimum values, the whole range, median, 75 and 25% quartile. But what you need to look into this particular data is that there is an asterisk with data number 11. So with the box plot, what it is evident is that there is one data in your, one value in your data sheet which is not lying close to the other values. And with the box plot, you can see asterisk with 11. Suppose if it is upper range data, which we will see in the next example, then it will come in the top. So here, what it represents is, what it will represent is 11th value in your data sheet is having outlier. Now you go in the data sheet and you can see here that indeed 11th value in the variable 1, because only variable 1 we are analyzing right now. Rest all are in the range of 235, 246, 240, 242, but this is only 24. Now if this kind of error is happening, then first and the foremost we should understand that this could also be because you have typed mistakenly, because everything is in the range of 230 to 240, 250, and this alone value is 24. So first thing, as I said, that when you are analyzing the outlier, you should be aware that you should cross verify whether you have done any mistake there or not. If you have done any mistake, you can change it and then again create the box plot. So let us suppose we change it with 244, because suppose if we left 4 in middle, and let us try one more time how this. So in descriptive statistics, in explore, leave everything same because it remembers from the time one you do, and then you created the box plot. Now if you see in this particular box plot, you will see that there is a median in the center. You have 25 percentile and 75 percentile values, and then you have whiskers, means maximum and the minimum values. And now in this particular case, you do not see any star or any dot. So it means now your data is not having any more outlier. So this was one of the example where you could see that an outlier in the minimum range. Now you will see in the data sheet that there is a variable 2 I have plotted here, and you can open this, analyze it again. So what you do is descriptive statistics, explore, and then instead of dependent list V1, you click to V2, leave everything same and press OK. Now you come down, because we are not interested right now into what it is there in the normal QQ plot and so on. We are interested to look into the outlier. So this outlier says you again in the 11th column or row, you have one outlier value which is way beyond your maximum value, right? So you go back again in your data sheet, because here in the box plot it is telling you at 11. So you go here and then you see that rest all are in the range of 230 to 240, and this is 290. right? Now, this is not too much variation considering that all the values are there in 240, 250. This could be a very genuine result, and you should be very critical before to remove this outlier. So options are that you can go for non-parametric test, and you can compare the result with the parametric test by keeping this outlier. And if there is any difference, then you go with non-parametric test. If there are no difference in the inferential statistics, then you continue with the ANOVA. Only thing is you will have to mention that there is one outlier in the sample when you are expressing your result. Now let us suppose the one option I showed you when you are doing the outlier in this that you can replace with the next largest value. How would you do that? So suppose you think that this you want to nullify the effect of this outlier. What you can do is that you can right click on the V2 variable in the data view, and you can sort by ascending or descending. Because right now if it is just 11 value, you can see that which is the highest or which is the lowest value. But let us suppose if you have 200 data points, then you will not be able to identify manually that which is the next highest value. In that case, you sort it by ascending or descending. Now, once you do the ascending or descending, you see the next value to the highest value is 250. And suppose you are interested in removing this outlier and making it to the next highest value, 250.12, you can change it with 250.12. But as I said that if you are sorting in the ascending or the descending order, it is better to keep little bit higher than the second highest value. So you can change it with 251 maybe. And then let us try one more time looking into the box plot how it looks. Now that you will see that the outlier is gone because you have manipulated, or you have changed, not manipulated, you have changed the data. So in this case you should write down in the result, but you can do it. This is one of the way that people are doing it. Okay, so this is about the outlier. So now that I have shown you that how the outlier data can be seen using the box plot, and there are one or two different ways that how you can improve your outlier in the data sheet, and again look into the box plot. So hope that this is clear. If so, we will move into the next topic. So close everything. No. We don't want to set this. We don't want to set this. Right? In the same Excel sheet, you will see that there is a separate page labeled as normal distribution. So since it's a practice workshop, I didn't give one data and then kept on changing it because that would have made it difficult to understand. So one data is for outlier, where you can see that how you can change the outlier, or you can express, or you can view it. The second is to look the normal distribution. Again, the normal distribution curve should be a bell-shaped curve. How would we analyze the normal distribution curve? If you remember, you can do the numerical or the graphical assessment by skewness, kurtosis, Shapiro-Wilks, histogram, and QQ plot. Let us do all four using SPSS and see that what is there in the how the data looks like. So again, the data is having two conditions. One is control, and another one is treatment 1, and then some variable which is measured. So we will open this particular data. normal distribution in SPSS. Similar way of writing here, you have the variables. Just remove this one and we will do it again. So you have the treatment, which is a nominal scale, and then in the value you have one that is stands for control, two that is stands for treatment, okay, right? And then you have one variable in the scale measure. Go in data view, and you will see that you have the treatment conditions and the variables. How would you do it? How would you do the analysis? Again, it's a part of a descriptive statistics in SPSS. You go in descriptive statistics, you do explore. Similar thing, variable is your dependent list and treatment is your factor list. Same box which we have opened for outlier, similar thing which we have opened now for normality. Click on outlier because we will anyway see whether we have outlier in the data or not. In the plot, we will look into the histogram. You remove stem and leaf because histogram will help you to identify whether your data is normal or not. And then we will also plot the normality with the different test. And the test we are doing here is Shapiro-Wilks test. You can do the transformation here, but we do not want to do the transformation right now because first we want to see whether the data is normal or not. Okay, continue. So now again I am repeating, treatment is your factor list, variable is your dependent list. In statistics you click the outlier, in plot you select the histogram and normality plot and continue. After that, in the display you want not only the statistics but also plot, that's why you select both. I hope that everybody is on the same page. We'll click OK. Again, the descriptive statistics we will see later about all this mean, median, mode, and other things. We will go to look into the normality test. Now, as I said that it does kurtosis and skewness test. So you will see that this skewness here of control is 1.56 with a standard error of 0.687 and kurtosis of 2.43 and a standard error of 1.33. So it means that it is positively skewed curve if you look into the histogram, and at the same time the data is widely distributed and it does not form a proper bell curve. Similarly, for the treatment one, you have skewness of minus 0.220. It means that it is negatively skewed, but it is not that much negatively skewed. It is more or less closer to 0. And at the same time you have negatively kurtosis, that is minus 0.363. It means that the data is not very widely distributed. Okay, it is sharp in the center, in the peak. So peakness is, if you measure the peakness, it is peak in the center. That's why it is negatively kurtosis. So this is the way. And if you know, if you remember, I showed you maybe not exactly the same formula, since these are advanced statistical tools. It may have slight variations, but more or less it follows the similar functions to calculate the skewness and kurtosis for control and for the treatment. Similarly, you have done another test for the normality. We will consider here Shapiro-Wilks test, which is widely used. And then in Shapiro-Wilks test, you will see the treatment one, it is 0.998. What it means is that it is, I mean, the normality, if you consider the null hypothesis, the null hypothesis is rejected in the case of treatment 1. It means that data is normally distributed, right? However, same cannot be said in the I mean in the condition of control, because the significance or the alpha value where we have considered as 0.05, it is lesser than 0.05. It means that the data is not normal. We have also seen in the case of skewness and kurtosis, it's widely distributed and positively skewed. Whereas skewness and kurtosis for the treatment 1 is not so bad. It is very much near to what normal distribution is. The same thing is reflected in the case of normality test. In this particular case, both are showing similar kind of pattern, but in some, I mean, when you do a number of tests, you will find that sometimes the kurtosis and the skewness is good, but then it does not follow the normality because of slight skewness and kurtosis. However, we will go further. So these two tests are numerical tests where you measure the skewness and kurtosis and the Shapiro-Wilk test. We will now go into the graphical mode of representation. Now, in this graphical representation, what you will find is that you have, if you, let us try plotting the, okay. So, in this case, with the histogram, so the benefit is that if you double click here and then there is an option for displaying the curves. So since for the normal curve this is the bell curve, you select that and then you will see the data indeed is not following a very good normal distribution because it is having a positive skewness. There are some data which is in the last quartile of the of this particular graph, like in the last 2.5%, right? So it is positively skewed. This we need to sort it out by doing the data transformation. We will be seeing now. But before that, we will also see the histogram for the treatment. Now, histogram for the treatment, you will see that it is indeed following a very good normal distribution, which was evident from your Shapiro-Wilk test and the skewness and the kurtosis. You do not have a very positively or the negatively skewed curve. So here in my screen, you can see the difference between a good normal distributed data set and then a positively skewed data set. Okay. Similarly, that quartile plot, as if you remember in the PowerPoint presentation, I showed you that a true data, I mean the observed data, is plotted against the data which should follow a normal distribution. In the y-axis, you have the expected normal values, normality distribution data from the normal distribution, and in the x-value, you have the observed values. Now, if it is a straight line, it means that it is following the normal distribution. Here, however, you can see that one particular data here. Here, which does not fall into the straight line. Now here in this case, this is a quartile plot for treatment, and you will see that most of the data points are following in the straight line, right? So it again tells you that you need to transform the data because one of the group in your data does not follow the normality distribution. One thing which you need to keep in mind, that whenever you are doing the data transformation, even though the data is not normal, I mean following the normal distribution only for the control, when you are transforming the data, you need to transform the data for control and treatment both in the same way. You cannot just transform the data for control or for the treatment and do the analysis, right? How would you do now? The transformation is, you are in the data view in the data editor of SPSS. You go and transform, compute variables, right? Now you give any name. Let's say that for positive skewness, what should be the first thing to do it? We will try with the log 10 first. Okay, so we will just write here log transform. Okay, this will come here, written here in the column. Now to do the transformation, you have to click on arithmetic, and then we decided to do log 10. So log 10 is this one. Now in this log 10, you take your variable and you put inside the parenthesis, okay, and then you click OK. Now that you will see that a log transformation of these variables are already here, right? So again you go in Analyze, Descriptive Stats, Explore. Instead of variable as a dependent list, you put log transformed as a dependent list and leave everything same. Click OK. In this case, what you see is that previously you had a skewness of 1.56 and kurtosis of 2.43, and now you have skewness of 1.40 and a kurtosis of 1.85. It is not the best skewness, because generally you should bring it to less than 1. So in that case, you should try with the square root, or you should try with the other arithmetic transformation. Okay. However, if you can see in the treatment one, it didn't vary much from the original one, because you still have slight negative skewness and slight negative kurtosis values. However, let us go and let us check that how is that. Okay, so in the normality test, in the Shapiro-Wilks test, it is not significant anymore. So it means that it has statistically, with the Shapiro-Wilks test, it has suggested that your data is now normal, kind of normally distributed, and you can go ahead with the t-test or a NOVA or whatever you have, whatever parametric test you want to perform on this data. You still have the positive skewness, which is evident from the skewness in the kurtosis value, but then in the Shapiro-Wilks test, which is based on the normal quartile plot, it suggests that you do have slightly better assumptions acquired or achieved. Okay, so this is how you do the data transformation. In case if you want to again try with some other type of data transformation, you go in transform, go in compute. Instead of doing the log scale, let us do with the square root or anything, or maybe, yeah, so you go with the square root. You select the square root by double clicking it, remove the question mark, and then again you put variable in between. Okay. Now you have a square root. Similarly, you go and then try with the descriptive stats and explore. And instead of taking log, you can take the square root. And same way you can check the skewness, kurtosis, superior test, and what else? Yeah, normal quartile plot and rest of it. So I hope that this is clear by now. That how should you do the data transformation. Let us close this once again. The last part we will see with the descriptive statistics. So again, with the descriptive statistics, you do the same thing. You have a file, this descriptive stats, you open with SPSS. Okay. Now you have two conditions, 1, 2. Suppose if you have three conditions, let's say you have one control and then you have treatment 1 and treatment 2, that also you can put it here as a third variable, as a third condition in the treatment, and it's the same way how you do the descriptive statistics. So you go here, treatment is your factor list, variable is your dependent list, you go with the statistics, go with outlier, select the normality plot, histogram, remove the stem leaf, and then you click OK. So once you consider all tests together, that helps you in the deciding whether you should go with the parametric or non-parametric. In the descriptive statistics, you will see that there is a mean. You know that how the mean was calculated, right? You can also cross-verify it it's a software, so definitely most of the time it won't be wrong. So there is no question of cross-verification, but you can try by using this Excel sheet, which I have already given to you. You can go and then use the Excel function and then check whether these standard error, mean, standard deviation, variance, median, these things are matching or not. Because sometimes if you go with the, let's say, interquartile range or even with the skewness, kurtosis, maybe the functions used in the Excel will be slightly different from the function used in the, or the algorithm used in the SPSS, so there will be slight variation in the result. However, it should be more or less similar. So that you can do, you can see that how the mean, which Aditya on the day 1 has explained us, that mean, median, mode, which is already there in the descriptive statistics. Then you have the variance. See the variance, it's here, right? You have this minimum range, maximum range. Minimum value, maximum value, range, interquartile range, skewness, kurtosis. So all these values all together, along with the normality test, histogram, is called as descriptive. Is a complete form of descriptive statistics, which helps you in deciding the parametric and non-parametric test. For the homogeneity of variance, so see again I am not showing you the same thing, because already 2 times in the outlier and in the normal distribution I have showed you how the different tables or how the different graphs you should see. So let us close this. I will open something different. So in the Excel sheet which I have sent you, you will see that there is a F-test variance, right? See, so this F-test variance is identified in the same way how you have seen here. See, so excuse me. So how you have seen is that for the control and for the treatment, you have calculated the variance using the function in the Excel. To cross-verify whether the variance function was perfectly working for us, I have also done here average, calculation of the, difference between the average and the sample value, squared it, sum it, and then divide by the total number. That is the formula which Aditya on the day one has showed you for the variance calculation. So this is already there. So if you would like to try that how the variance can be calculated in the Excel sheet, you can go through with this particular spreadsheet and practice if you want. So this is about how you do the descriptive statistics uh, and the parametric test assumptions in SPSS. It will not vary much even if you are going to use it other software. As for example, I will show you in the past because I assume that not all will have the SPSS. So let us try once with the past in a couple of minutes. So you open the past, and if you remember on the day one I showed you how to do the data entry. For this we will just paste it here, right? So you have 1 and 2 which you can attribute it as group because this is a two different group, and this is a numerical data, so you leave it as you leave it as it is, and then you click you select the column A and column B, and then you do the summary statistics. Now in the summary statistics, you will see that it is giving you what SPSS has gave you, total number. So total number, that is 10 and 10 in both the conditions 1 and 2. Minimum value, maximum value, sum, mean, standard error, variance, standard deviation, median, 25 percentile. If you remember that 25 percentile means a value from where the less than 25% of the value lies. 75, it means that above 25%, that the value above, from where the 25% above values are there, that is 75 percentile. Then you have skewness, kurtosis, and then coefficient of variations. So this is how you do the descriptive statistics, or descriptive statistics in PAST. But you will see that this descriptive statistics has not given you the histogram and other thing, for which in the past you have the option go in plot, okay, in histogram, and you will see that it is giving you two different bars. Why? Because it is not able to separate the two groups. So let us try with just one independently, plot, histogram, and now you will see that this is the, you can increase the number of the bins here. Bins means the class, and then you have the frequency. It means that between 155 and 162 you have 4 values likewise. So you can again fit the normal and then see whether the data is normal or not. Then you can see that it indeed is having some positive skewness over here, right? So this is how you open the histogram in the past. There is also box plot, which helps you to identify if you do have the, okay, here, which helps you to identify if you have any outlier or what is the range of your data set. So here you can see that you have the box plot. You can click the box plot, mean and whisker. So this is the mean value, but if you just click box plot, This is the median value. This is the 75% quartile. This is 25, and then you have the whisker range, complete range of the data. So this is how you do in the past. What else is remaining? Yeah, maybe normality plot. So for normality plot, again, you will see that normal distribution, normal probability plot is there, and this is here. So this is more or less similar to how you have the QQ plot. Right? So if everything is within the straight line, then the data is normally distributed. Then okay, so there I could not show you the F test because in SPSS what happens is that homogeneity of variance is combined when you do the t-test or the ANOVA. It means that you cannot do separately the homogeneity of variance test. But in PAST, if you click on the group that is 1 and 2, it means that two conditions, and then you go in univariate and then go with two sample test and two sample test here. So this will give you number, mean. I mean, this is the t-test, go in the f-test, which is for the equal variance, and this, the data is showing that it does not follow the equal variance because you have the no. So anyway, so I will show you that how this f-test is there in Excel. So you open the t-test and then you will find that there is one more spreadsheet which I have already done in the afternoon, and you will see that, and you can match that how the two different okay, so here you see the variance for the first first condition is 84.338, which is coming with the variance function in the Excel. Similarly, for the variance function in the second condition, you have 19.183, right? So in this way, it calculates the variance, and then this variance, the ratio of this variance, which is 4.397. So the this ratio of 4.397 is matched with the critical value. So for the critical value, I showed you that there is a table. So you match with this critical, table, depending on what is your degree of freedom in numerator and denominator, then you can match. If the value f is greater than your critical value, then it means that the data, there is test, this is equal variance. So the data is having the equal variance, right? So likewise, you do the, the null hypothesis is rejected, so data is not having the equal variance, which we have already seen in SPSS, that data is not having the equal variance. And we will further see tomorrow when we will perform the ANOVA and t-test. So that is it, what I wanted to show. Hope that you get the things, and yeah, so pretty much this is what I wanted to show you today. All the descriptive statistics and assumptions using SPSS and PAST with the theoretical understanding.